messed up that transition again, didn't I? Okay. I'll fiddle with that later. Right, I don't know if this is going to be jittery. I don't know how well the video is going to come across. Good evening. Welcome to Physics with Keith. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 programs running, 7 of which are very intensive on my GPU on my laptop. So if it's really jittery, let me know and I can come up with a plan B. But hopefully this is going to be clear enough that you can see what's going on. Yes, because today we're going to be looking at waves. So this is your first time to a Physics with Keith tuition session. The way this works is I'm on YouTube, I'm talking to you through your TV, through your phone screen, through your laptop screen, but you can interact and you can see plenty of people already interacting over here on the chat, and that chat is in Discord. So if you follow the link in the video description or the live YouTube description to Discord, and you can get yourself in this channel and then you can interact live. Now, I'm going to be asking all sorts of impromptu questions today, but I'm not going to be using any formal exam questions. And I'm going to really encourage you to participate, to ask questions of your own. We're going to be looking at waves today, and it is a challenging topic. It doesn't need to be, but it is. Students do find it challenging. And as you saw in the chat that we were discussing before, waves underpin so much of physics. And it's also an area fertile with misconceptions. And that's why I wanted all these simulations running. Now, nobody's commented to say that it's too jittery or too laggy, so I'm guessing that means that my computer's just about holding on to it, which is good, because you wouldn't believe how many programs I've got open right now. This was a risk. So I guess that means it's okay. So with that said, let's bounce across and I'll show you the first simulation. That's great. Okay, glad to hear that, Wombat. Thank you. And hello. I don't know if I've said hello to you yet this evening. Hello. And hello to Charles. Sorry, I didn't get a chance to say hello to you in the chat because I only had about 5 seconds left before we started. Yeah, so what I'm going to do, I'm going to use some simulations today. I'm going to use the simulations that were made by Dr. John Nunn of the National Physical Laboratory, who very kindly said that I had permission to use them in these tutorial sessions. I've got the email to prove it. So I'm going to be using those simulations, and we're going to work through and explore together some of the properties of waves, some of the important features of waves. Now let's start with what makes a wave a wave. What is a wave? Hopefully there's not too much movement on the screen. This is still transmitting okay. What makes a wave a wave? Well, I'm going to open that question up to you. What is it about waves? Why do they deserve their own section on the syllabus? What is a wave? How are waves different to anything else you'll find in physics? It's a really open, vague question. I'm really interested to see what you say. You could answer the question with just one word and get it right. Is it about waves? What are waves? So I can see one person's typing, 2 people are typing right now, which is good. Just taking a gentle swig from my mug. No reason why I'm showing that. So we've got an answer from Wombat there. Transfer of energy when no matter actually moves. Well, matter does move, but it isn't transmitted. Pranav saying energy, no net transfer of matter, no net movement of matter. Waves are vibrations, says physics are. Yeah, there's a few different answers there. You're missing one key thing that makes waves special. And that is the idea of superposition. Now, GCSE students out there, you may not have heard that word. I know there's some GCSE students tuning in. Interference, exactly, Wombat. So some GCSE students out there, you may not have heard the word. If you're a GCSE student, let me know. Have you heard the word interference or the word superposition within your physics lessons? And the reason why many students haven't heard it is because for some reason, yeah, brilliant. Well, your computing teacher, if I think it's who I think it is, your computing teacher is in fact a physicist, and that would explain it. Freya, no, exactly. Now, one of the reasons is that you won't find the word interference or superposition in GCSE textbooks or revision guides, and yet that is what makes waves special. That's how waves are different. And it works like this. If I have two particles, two lumps of matter traveling towards each other. Let's just draw this quick sketch out here. If I have a lump of matter here and a lump of matter here, and they are traveling towards each other with a head-on collision, what do you think the outcome will be? What's going to happen if I watch this picture for long enough? Maybe these are two bouncy balls or two bowling balls or something. Anyway, they're moving towards each other. What am I going to see happen? Yeah, exactly. Transfer of energy, transfer of momentum, collision. So there's going to be a transfer of energy and momentum through that collision. Energy will be conserved. Momentum will be conserved. Momentum's always conserved one back, whether it's elastic or not. If it's elastic, kinetic energy is conserved. They collide. Don't worry about the waves at the moment, physics are. We're just looking at... If you want me to call you by your real name, physics are, let me know. I'm just calling you that because that's what your screen name is. Balls rebound in opposite directions, or of course they could end up sticking. That's okay, Wombat, I get that. Or they could end up sticking together. That's a possibility as well if they have an inelastic collision. I can use your real name. That's great, 𝗟𝗲𝗲. That's good to hear. So if they could stick together, but what's not going to happen? They're not going to pass through each other. They're going to interact in a way that means their momentum is going to change. The one on the left is going to experience some change because of that interaction with the thing on the right. That's not what happens with waves. That's how waves are special. Because with a wave, if you imagine this is a packet of wave, I'm just drawing it as a circle right now to keep things as simple as I can. A packet of wave, whatever that means, traveling this way. And here is a packet of wave traveling this way. What happens is they pass through each other and then come out the other side. And the wave you see coming out the other side is completely unchanged by the interaction. So this wave here, whatever it looks like, after the collision will look exactly the same thing. It will look exactly the same, as you can see with this identical diagram I've added on the bottom. And this thing here, which I'm going to represent with a picture of a cat, there we are. That is clearly a cat. Then after the interaction, after they're moved through each other, you'll notice it's exactly the same. Okay, I'm not an artist. It's exactly the same size. It looks exactly the same. There's a cat coming out the other side. The two waves are completely unchanged by the interaction. That's not the case with matter. Thank you, Pranav. So that is how waves are fundamentally different to anything else you'll see in physics. So I'll ask that question again. What is a wave? Now, a few of you gave me answers when I said what's special about a wave, what makes waves special, what is different about waves. But now I want to know what this thing actually is. This thing I've drawn a smiley face on, this thing I've drawn a cat on. What is it? What is a wave? This bizarre thing that can pass through another wave and yet be completely unchanged in the process. What is it? What do you think? GCSE students, don't let the A-level students hog all the fun. Join in. What is it? What is a wave? Fluctuations, says Ben. I like that answer. Fluctuations in what, of course? That's the next question. Disturbances, sure. They travel through, I think that might be trying to say, through a medium. Oscillations of matter. fluctuations in their respective force fields. Of course, Pranav, you're talking about one particular type of wave, and Wombat's talking about a different type of wave. And they're both waves. They're both waves, aren't they? So if we want to define what a wave is, that we're going to have to do it in some other way. And the easiest way to do it is graphically. Now, when you get onto A level, and I will write this out for you as well, we can represent what a wave is algebraically, but at the moment, we're only talking about GCSE level, so we are going to show you what a wave is graphically. So let's scroll this down a bit. Hello. One of my later simulations just appeared. And it really is straightforward. You don't have to get too spooked by this. Come on. Oh, OneNote is really struggling with the so many apps open. I might not be able to use my little arrow tool. That's a straight line, by the way. Okay, so if I wanted to represent what a wave is, I need to draw a graph. That's the first thing. It's a graph. These are perfect lines. On the x-axis, I could have time, perhaps. Or I could have distance. Let's put x to indicate it's a spatial thing. I'm looking in space. And in the y-axis, I could put all sorts of things. I'm going to leave it blank for now. What is a wave? It's this. That's all it is. It's a sinusoidal... Oh, dear. Oh, I'm not happy with that. I'm going to have another go. Come on, we can do this. It's really struggling. Okay, that will do. There's so much lag on my computer as I'm doing this. If it is transmitting okay, I'll be amazed. It is a sinusoidal variation in something. That's all it is. If it is a mechanical wave, apparently it did, Pranav. So if it's a mechanical wave, like Wombat described, an oscillation of matter, it looks like cos to me, yeah, but we could still describe that as sinusoidal. It's just been shifted by 90 degrees. But yeah, Wombat, of course, that is a cosine. But cosines are sinusoidal. So what I could say on this y-axis here, I could say this is some sort of spatial displacement. I love using big language, technical language. GCSE students, calm down, it's okay. Spatial displacement, something is moving in space. And what we can see here, I've labelled that Y. It doesn't have to be labelled Y. It could be labelled S for displacement. We know S is displacement in mechanics. What's happening right now is something is being displaced in such a way that it's moving backwards, then forwards, then backwards, then forwards. We can call that oscillation. So right now I've got a graphical representation of a wave at a snapshot in time. Don't forget, you can ask questions at any point. I'm encouraging you, please ask questions at any point. Instead of watching a wave, oh, I mean, it didn't quite come out like you wanted it to, Pranav, but, you know, the thought was there. Instead of having a snapshot in time where we look at how the displacement of matter changes over some distance, we could have temporal displacement. In other words, I'm watching a particular little piece of matter and I'm watching it oscillate. I'm not looking at how it changes in space along where the wave is moving. I'm just watching this piece of matter over time and sort of plotting a graph of its displacement versus time. Oh, not a problem at all. Not a problem at all, Edward. How did it get on? Great success, I hope. So that's what a wave is. Now, that's quite difficult to express to a GCSE student. So we use concrete examples of waves. For example, we have mechanical waves. 2 PV. Well done. That's very impressive. Right. So, for example, we've got mechanical waves that Wombat was talking about. A tangible example. And here's a tangible example of a mechanical wave. So here's a string, and I can move this string. In fact, what I'm going to do is I'm going to switch it to automatically oscillate like this to keep it nice and simple. This may be quite laggy because this is quite graphically intensive, but we'll see how he gets on. Let's just stop the string for a second. Well, that did not stop the string at all. Okay, this simulation isn't quite working with all of my apps running. If you're tuning in late, I'm doing an experiment where I've got about 15 programs running, 7 of which are graphically intensive it's graphically intensive things for my graphic card, and I don't know if it's working okay. So if it's coming through jittery, my apologies. And maybe that might be the case. What if I hold it? I guess that's what I'm doing at the moment, Pranav. Yeah, great. Okay. So what you can see, if I let go, you can see that we have a particle, one of these yellow dots, which moves up and moves down, and it moves up and it moves down. If we just watch one of those particles, I'll just stop it for a second, let the string die down. Should be a way of increasing damping so that it doesn't reflect. Let's whack damping up really high. There we are. That might help. So if we just watch one of these particles, just pick a yellow dot near the left-hand side and watch what it does. It moves up and down. That's all it does. So if I watch it over a period of time, I'm logging in from my personal phone and I cannot hear anything. Okay, Sebby can't hear anything. It's probably because he's not looking on YouTube. So I'll just pop the link to YouTube there. There we go. Hopefully he'll realize that that's where it is. So if you watch one of those yellow dots, it's just oscillating. It's just oscillating vertically. So if I plot a graph of what the vertical displacement of that yellow dot is every 10th of a second or every 100th of a second, or I've got a stopwatch in my hand, so that's what I'm doing with my hand. It's my mime for I'm holding a stopwatch. So every small interval of time, I record what the displacement of that yellow dot is and plot it on a graph. I will get a sinusoidal wave. But likewise, what I can do is I can get this thing oscillating. Let's turn the damping down a little bit because it's a little bit miserable at the moment. I can get this thing oscillating and then I can just pause time and have a look at it. Now, I don't know how to do that on this little simulation, but let's imagine I paused time and we had a look at it. And if I did that, then you would see that there's this wave going up and down. And at a particular instant in time, where on the left and right direction, we'll call that the x direction. Now, this is a mechanical wave. So what I can do is I can actually set mechanical waves to go in opposite directions. Let's switch this back to manual. Let's stop my string from moving. Let's turn damping right the way up for now, just so I can get all the energy out of my string. Right, let's turn it right the way down now. I could have screenshot Pranav, yeah, but I'm not going to. So let's put a wave in this string. There we are, that's a wave. And let's put another wave. And if you watch these two waves, watch what happens as they move through each other. They come out the other side completely well, they should do if the simulation's working right, completely undisturbed. It's not quite right because we've got some damping here. Let's speed the wave up a bit. Let's stop the string. And let's try that again. If I send this wave that way, and I send this wave this way, then they will go past each other. Well, right now they're cancelling each other out. Let's stop the string. So that's what's special with waves. Now, one way to think about a wave is not as a tangible thing that's moving, because it really isn't, is it? There's nothing tangible moving from one side to the other. It's to think of it as an influence. And so every one of these yellow dots experiences an influence from what's happening to the left of it and an influence from what's happening to the right of it. I don't know where the string's going now. And those two influences add together. So if the wave coming from the left is telling one of these yellow dots, go up, and the wave from the thing on the right is telling one of the dots to go up at the same time, the dot goes up twice as far. But if the thing from the left is telling a dot to go up, but the thing from the right is telling the dot go down, then it does neither. both of those influences get added together. And we can see that mechanically. It really does, doesn't it, Pranav? It really does. And that's what makes waves special. It's called, so similar to Fourier. We'll come on to Fourier probably just after half term, Edward, probably. Yeah. But no, what it is a wave is the addition of these two or more influences. And the easiest way for me to show that, and I'm going to get rid of this simulation now, so as I move through today, things should get smoother and smoother as I shut more and more of the programs I've got open. At least that's the hope. So if I go back to this program, which I was showing you before, what this is really clever. I'm showing you 6 different sources of waves arranged like this. And from a distance, you couldn't tell it was 6 sources. It would just look like one source right in the middle. And the reason for that is at every point in this space around here, where my red dot is moving around, at every point, we're adding up the influence from all of those dots, from all of those sources. It's called superposition. It's the reason why you get things like diffraction. So let's close that one. We don't want that one anymore. And let's move to a nice diffraction. Here we go. A nice diffraction simulation. So I will just want to get rid of one of these. Is there any way I can get rid of it? Probably not. Let's put them both in the same place. That's the easiest way to get rid of it. Nearly. Okay, I mean, that's close enough. So what you can see here is waves spreading out. Simulation speed. Yeah, we could turn it up. Usually when you run a simulation more quickly, it makes it less accurate, but we're not that bothered about accuracy with this because it's just a little cartoon. Should we put this back on top of the same place? So what you can see here is the waves are spreading out. So GCSE students, have you heard the word diffraction? Diffraction. Yeah, it's supposed to say speed. It's obviously a typo. Yeah. You've heard of diffraction, yeah. So this is diffraction. This is what diffraction is, the spreading out of a wave. And it's caused by that effect I showed you before. If you have multiple points producing a wave, then some distance away from it, you add up the effect of all those points and you get the resultant effect. If you do that, it causes the effect to spread out, the influence to spread out. So that's what diffraction is. Diffraction is a consequence of interference, which is a uniquely wave property. I mean, if you look, if I put these two sources of waves next to each other, then what happens? Exactly! Exactly! Huygens Fresnel principle. Nice! Well done, 𝗟𝗲𝗏. I'm really impressed. So I'm not allowed to give house points while I'm on Physics with Keith. This is not endorsed by the school I work at. So what we can see here is two sources of waves. It's brilliant. It's really impressive to see. At any point along this line down the middle where my red dot is, because it's the same distance to each of the sources, that's these things over here on the left, this and this are both sources producing waves. At any point, what's happening now is we are adding up the effect of those two sources, and it's even stronger because you get them both. Whereas here, those effects actually cancel out, and you end up with no effect, which is why the wave seems to be, well, there's no wave here. There's a wave here, but there's no wave here, and so on. A uniquely wave property. Right, well, that was good fun. And very briefly, I'm going to ask you to give me examples that you know from physics where waves becomes an important principle. And while you're typing that, I'll get the next simulation loaded. So, areas of physics where waves is essential. What's going on there? Standing waves, yep, stationary waves or standing waves is the known wombat, exactly. And we can come on to that in a little bit. Huygens principle, or Huygens-Fresnel principle, the idea that's superposition of the wavelets from an infinite number of infinitesimally spaced, I'm getting ahead of myself, produces these wavefronts. Polarization, yeah, polarization, I agree. Sound waves. Do you know what, Edward? Yes, sound waves. Absolutely. So transmission of energy by the vibration, by the variation in atmospheric pressure. If you're in air, sound waves don't need to be in air, of course. Any medium can transmit sound waves. But yes, Fraunhofer diffraction, absolutely. Or otherwise known as just diffraction. Yeah, so diffraction, sound waves. I mean, there's all sorts of principles you haven't mentioned yet. You haven't mentioned water waves. That's a superposition effect. You haven't mentioned tides. Now think about tides. The sun is tugging on the Earth, so there's going to be an effect there as the Earth rotates, and the moon is tugging on the Earth. Sometimes those tugs are in the same direction, sometimes they're in opposite directions, and the resultant influence is what we observe. So even the tides, Bragg's law, so we're talking about diffraction, absolutely. Snell's law, so you're talking about refraction, absolutely. I'm thinking of other examples of where two effects, we'll come to that, Sebi, I've got a simulation for that, but we're talking about where two effects come together and superpose rather than particles colliding. Tides was a really good one. Yeah, Doppler effects, yeah, there's loads of examples coming out. Gravitational waves, absolutely. Light, of course, light. You can have two laser beams shining through each other. They don't collide with each other, do they? It's not Star Wars. They move through each other. Double slit experiment, which you've just seen, yeah? Okay, so let's think about sound for a second. Has anybody got a music player with two speakers? Electron diffraction? Oh, absolutely, 𝗟𝗲𝗄𝘬. Yeah, absolutely. So has anyone got a music player with two speakers? Great, okay. You can do an experiment. What you can do is you can get yourself a... Yep, great. Okay, so you can get yourself an audio recording of a particular frequency, and you can just find frequency generators online. You don't have to hunt far for it, or just use Audacity as a piece of free software that you can use to do this. Play it through those two speakers, space them apart, and you'll be able to hear where the two influences from the speakers, certain places in the room, they'll agree, they'll add up, and the sound will be even louder, and certain places it will be quieter. I'm playing through two speakers. I am privileged. I'm afraid I don't have a stereo mic, so you're not getting the full benefit of that, but yeah. So let's just go to a quick equation now. This is an equation GCSE students have to memorize. You might have seen it with a V instead of a C, but I'm using a C, equals F. It's still a little bit laggy on my computer, but it's certainly improved. Still a little bit laggy. So there's our equation for wave speed, and the wave speed is calculated by the wave frequency. That's how many times the thing, whatever the phenomenon is, with sound waves, it's pressure changing. With the string, it's the string going up and down. I love this. Yeah, Wombat's absolutely right. Technical name for when it's the two influences agree is constructive interference. So I'm going to try and keep it GCSE today, but what you've said is right. And after the half term, when we go on to waves 2, we're going to be going into this sort of thing in much more detail. Right now, this is a very overarching introduction. Yeah, so this is the frequency. So this is how many times frequency. I'm not seeing it in radians, hertz. Yeah, but you'll get used to it. If you want, okay, so Pranav is offended by that. So we're going to go ahead and use this. And that might make you feel a little bit happier. I've done something wrong there, haven't I? Yeah, that should equal 1 over that. So let's, there we are. So hopefully that makes you feel a little bit better. Happy with that, Pranav? That bit on the right is just for Pranav, no one else. Oh, right, okay. Okay, I'll take that bit off. I'll try to take that bit off. It's not erasing for some reason. Nope, sorry. Microsoft had other plans. Okay, so frequency. Fine. The lambda, the Greek symbol lambda, that's the wavelength. That is the physical distance between one maximum of this phenomenon and the next maximum of this phenomenon in the direction that the energy is being transmitted. And c is not necessarily the speed of light. It is the speed of light. That's an example. But it's any sort of wave speed. So let's use the example of sound. Who knows roughly what the speed of sound is? Roughly. See if anyone happens to know. We're going to do it in meters per second. So 303 is a little bit on the slow side. I'm talking about in air, of course. Yeah, 343 meters per second or 330. We're going to go with 330. It's around about that. 350, yeah, that's the sort of a top end of it, perhaps. It depends on how humid it is. We're going to go with 330 meters per second. That's the speed of sound in air. Does anyone happen to know what the frequency is of, I think it's a concert pitch, but don't quote me, of an A above middle C? Anyone happen to know? In case you're wondering, I think it's A4, what they call the A. Yep, 440 hertz, absolutely. 440 hertz. So a straightforward question that I want everyone to answer. If you're a GCSE student, you can grab your calculator. You might not need a calculator for this. I think you could perhaps solve this in your head. But I would like to know what the... Yep, 440. Okay, so I would like to know what the wavelength is of this radiation. Of this sound, sorry, it's not radiation. Well, I suppose it is radiation. This sound wave. What would the wavelength be? Yeah, exactly. About 75 centimeters. 0.75 meters. Perfect. Brilliant. It's about 75 centimeters. So if that is the wavelength, okay, that means that I can get significant diffraction of sound waves if I try to force of concert pitch A, if I try and force it through an aperture of that sort of size, that sort of diameter. It's not an exact thing, but it's that sort of diameter. I'm going to get significant diffraction. Of course, it raises some questions. My speaker is smaller than that, so what's happening there? I'll leave you to ponder that one later. What that also means is that if I set up my speakers, so I set up my speakers like this, one on one side of the room, one on the other, and they're connected with exactly the same length of wire, although actually it doesn't matter for this particular experiment, to my sound making machine, a hi-fi, a stereo, I don't know what you call it, a radio, a CD player. Do you still have those? I've gone off the bottom of the screen. A sound making machine. These are speakers on each side. And I play that sound so that the sound is traveling in these directions like this. Like this. How far do you think I'd have to move my head from when it's loudest? This is my head. Let's say it's loudest there. How far would I have to move my head in this direction before it's loudest again? What do you think? A-level students might know this. I don't understand what you've written there, Pranav. I'm sorry, I'm struggling to understand that. Yeah, Edward, that's the same sort of thing that Pranav said. I've got frequency 440 hertz playing through both of these speakers. They're pointing at each other. And I've got a really loud sound. How far do I have to move my head? The sound will go quiet as I move my head. How far do I have to move it before it goes loud again? So, Ben, you think one wavelength? Ritva thinks 1.5 wavelengths, or is that 1/2 a wavelength? It's not clear. Give me a distance. Give me a distance in centimeters if you like. Meters if you prefer. So, James, you're saying that if I move it 37.5 centimeters, it goes quiet, and then another 37.5 centimeters, it gets loud again. Is that what you're saying? Oh, I see what you're saying, Pranav. No, let's assume that the speakers are sufficiently loud and big, and I'm sufficiently far away from each other that the effect of the attenuation of the sound because of moving away from one speaker is negligible compared to the interference effect. It's just the interference effect I'm interested in. No one's actually said the right answer yet, which is fascinating. I'll tell you why it's fascinating. It's fascinating because I know that there are A-level physics students taking part in this. Absolutely fascinating. Yeah, James, that's what I thought you said, and that's still not quite right. No, that's not right either, Edward. Yeah, the center, let's say the center is the best point, Pranav. And let's say that as I move away, the attenuation effect because of moving away from a particular speaker is negligible because they're sufficiently far away that the inverse square law means that small difference doesn't make that much of an effect. But I still hear it get quieter and then louder again. How far do I have to go before it's louder again? And so far, no one's got it right. Okay, I'll give you a clue. So you all are convinced that you'd have to move the distance one wavelength. That's what you're all telling me. Ben has now got it correct. It's half a wavelength, and hopefully this picture will show you why. So let's imagine on the left we've got a speaker that is emitting the yellow wave. And on the right is a speaker that is emitting the blue wave. Remember, the waves are just a graph, a graphical representation of a sinusoidally varying phenomenon. That's all it is. The green wave is what happens when I add the blue and the red wave together. GCSE students, make note of this. Look, the blue and the yellow waves are going through each other, but they are not changing each other as they do so. The green wave is what we actually observe. It is the resultant influence. So if I freeze it at some point, it's too slow. Let's try again. Freeze it at some point. Can you see that the two influences at this instant in time completely disagreed? Superposition, otherwise known as interference, meant the resultant influence was 0. But if I then wait, now at this instant in time, the two influences from the left speaker and the right speaker, they now agreed. And so we get this uber influence, the sum of the two, the green one. Now what I want you to watch is how that influence, which is a wave, it's a sinusoidal oscillation, you know, this thing is running, and if I plotted a graph of the displacement of the green line at a particular point versus time, it would be a sinusoidal wave. All right, you're looking across space and time is running, and that's why the thing is evolving and changing as we watch. But if I were to watch a point on this green line, it goes down, then it goes up, then it stops, then it goes down, then it stops, and I plotted that on a graph, it would be a sinusoidal wave. Can you see that the maximum displacement here of the green wave is far bigger than it is here? In fact, here, if you watch where my cursor is, the blue and the yellow wave always disagree. Whenever one says go up, the other says go down, and vice versa. So the green part of the wave, the green wave, the superposition of the other two, gives you a displacement of 0 at all times. Whereas the green wave here, at this position here, can you see the blue and the yellow always agree at this position here? The blue and the yellow always agree. So the green wave, the superposition of the two, has a much bigger maximum displacement. So where my cursor is now, the air is shaking around like crazy. But where my cursor is now, the air's not shaking around at all. So if I put my ear here, it sounds loud. But if I move my ear to here, it sounds loud again. And I will freeze it just for a second. What is the distance from one time where it sounded loud to the next time it sounded loud? And it wasn't one wavelength. As Pranav has said, as Ben said, it's half a wavelength. Absolutely fascinating. Half a wavelength. If you have questions, please do ask them. I'm a friendly face. I know physics, and I'm happy to help you. You've got to ask questions if you need any help. Okay, GCSE students, on your keyboards. A-level students, do not touch your keyboards. GCSE students and below. I'd like to know what we call the maximum displacement of the wave. Oh, A-level students, you can type a question. You can do that, but just don't answer the question I've just asked. So GCSE students and below, what do we call the maximum displacement of the wave? Because I've deliberately avoided saying the word. Well done, 𝗟𝗲𝗲. Well done, Lex. Amplitude, absolutely. Yeah, Pranav, but remember that these are both oscillating. So you can take the intensity is proportional to the square of the amplitude. So the intensity would be the same at this antinode as it is at this antinode. So my apologies to those of you who are GCSE students. Pranav is asking a question or making an observation about the relationship between amplitude and intensity for stationary waves. So I used some A-level technical language there to help him understand. But yeah, Edward's right, Lex is right, 𝗟𝗲𝗲 is right. It is amplitude, maximum displacement of the wave, as measured from the equilibrium position. Yeah, amplitude is not the distance from the top to the bottom of the wave. It is, well, it's half that. It's the maximum displacement of the wave. And so you can see that at this instant in time here, the displacement of the wave at every point is actually equal, the green wave I'm talking about, is actually equal to the amplitude. But at this point here, can you see that the displacement of the wave at every point is, well, as close as I can get to 0. So the displacement of the wave is varying sinusoidally, but the amplitude is that maximum displacement. And the amplitude of the wave varies along this wave because it is the superposition of two waves moving through each other. And that is an experiment you can do at home. You can get your two speakers, you can set them up, you can get your 440 Hz concert pitch A using something like Audacity, play it through the two speakers, space them far enough apart, put your head in the middle, close one ear, and then move your ear along. And it should be around about 37.5 centimeters between where it's loudest and then where it's loudest again. Test it out. Do the experiment yourself. The sound waves don't collide with each other. Right, okay, let's move on to a slightly different topic. Again, bringing it right back to GCSE level. Here's a simulation of a wave moving across the screen. And I've got a timer here. And I can start that timer. I don't know why the timer isn't running, but I can start that timer. It's a very simple thing I want you to do. I'm going to press start, and I'm just going to leave it running. And I want to know what the speed of this wave is. Now, are you able to calculate it from what information we've got on the screen? We'll find out. I don't think we can calculate it from the information we've got on the screen, but we'll see. We can get the frequency from that, but we don't know what the wavelength is. Ah. It's an interesting one, isn't it? So, who counted the number of waves that went past per second? None of you? All right, let's try that again. This time, don't worry about the wave speed. We'll deal with that in a second. Let's just measure the frequency. Oh, you counted them. Brilliant. We'll do it again. Oh, interesting. We'll do it again. I would like to know what the frequency is. And I'll do it as well. I'll play along. Ready? I'd like to know what the frequency is. You're all telling me how many waves you counted, which is good. You have to put a bit more information together there. I counted 11 waves, by the way. So I'd like to know what the frequency is. Well done, Lex. Spot on. And you were the first one in there as well. Brilliant. Look at that. James has got it. Joe's got it. Wombat's got it. Jonathan's got it. Yeah. Frequency. So first thing you work out is the time period. Very straightforward to do that. If we've got 11 waves in 20 seconds, then how long did it take to get one wave? 20 divided by 11. Then you take the reciprocal to get the frequency. And it looks like you've all done that, and that is fantastic to see. Right, now I wonder if we're told how long the tube is. Yeah, I think we've got as much mileage out of this as we can get, because I don't think we actually get enough information. Ah, hello. Ooh, fascinating. Okay. We've got the frequency. I've paused time and a ruler has appeared. That's about as good as I can get. Okay, so I would like to know what the wavelength is. It's unlikely to be in meters. 20 meters is quite a long experiment. I think it's more likely to... Oh, my hand goes off the side. Hey, look at that. No, I think it's more likely to be centimeters. Yeah, no, 20 millimeters would be a bit on the small side as well. So I think this is most likely to be in centimeters. I mean, given that it says here, enter wavelength centimeters, I think that's centimeters. You reckon the frequency was 0.55? You reckon it's 4 centimeters? Right, what was the time period again? So let me take the reciprocal of that. So about 1.82, let's say. Okay, so finally, you've got all that information. We want the wave speed in centimeters per second. I don't know if you can see all those numbers there. So what is the wave speed? It wasn't 4 centimeters per second. Remember the equation? You can just see it poking out through the top of here. If I move this down a bit, it will reveal the equation. Oops. Scrolled a bit too far. Oops, didn't scroll far enough. And my simulation has vanished. Come back, simulation. There we are. So we're all saying 2.2 centimeters per second. Yeah, we just times the two numbers together. Let's see. And let's all cross our fingers and hope that that Dr. John Nunn agrees with you all. Well, we got one of them right. Apparently, we didn't know the frequency. Well, I don't know why that is. It is, however, possible that that was partly due to the fact this thing was lagging like crazy. So I'm not going to lose too much. I'm not going to lose too much sleep about that. Is there any other numbers you want me to try in there? Shout now. Oh, hello, Dvorak. I hadn't noticed you'd come along. Well, I don't think it was, but I'm really tempted to recheck it now. Time is against me, though, but I really want to recheck it now. I started counting from 0 to make sure that I didn't miscount. Maybe I did miscount, though. Who knows? You want to try 0.5? All right. No, still not happy with that. So I think we're just going to leave that. Okay, you're all telling me to try these numbers. Try again, try again, try again. Yeah, I think the thing was lagging to such an extent that I don't think we can trust the timing of it. I mean, look how it was. Oops, look how it's moving. It's lurching and all the rest of it. I think we should just call that a day. I was happy with your 2.2. I agreed with your 2.2. Dr. John Nunn doesn't, but never mind. Okay, so last thing we're going to look at, and I'm going to close this simulation because we're not going to do that one now. Is this? This is really pushing my ability to transmit video when there's lots of small things moving on the same screen. So I don't know if this is going to work. If this is really lagging, do let me know. Remember, I wanted to do a bit of an experiment today to see how this will work. I will be watching this back later to see how good the video was. It looks okay. It's incredible. There's smoke coming out of my laptop. It's quite clear. That's brilliant. Okay, longitudinal transverse waves. You can see what's happening. It's good. You can see what's happening. So A-level students, sit on your hands so you're not tempted to write a perfect answer for a second. GCSE students and below, I would like you, in the best scientific English you can, to describe what a longitudinal wave is and describe what a transverse wave is. Essentially, I need 2 sentences from you. One for a longitudinal wave, one for a transverse wave. The downside, don't want to spook you, but while you're typing your answers, Pranav, I can see it says you're typing. You are not a GCSE student. Sit on your hands. While... exactly, yes. While you're typing your perfect description of a longitudinal wave and a transverse wave, I'm just going to waffle on for a second. The bad news to you is that these are some of the few things you've just got to memorize. There's not a lot in physics that you need to memorize. Most of the time, physics is about problem solving, applying first principles. Students who know me from school know that I do not have a good memory. In fact, if you're sitting on your hands and you want to confirm that that is the case, go ahead and type the confirmation that I do not have a good memory. But I can do physics, and I can do physics because I can solve problems. This is one of the few things that I had to sit down and commit to memory. Dvorak, I like your answer. Ritva, have a look at Dvorak's answer, and I think you'll see what is... Oh, come on. All right, okay, let me get my fingers out. 63. Yeah? I know the finger trick. 63. Trying to trick me with the times tables. So longitudinal waves are when displacement, like it, is in the same direction as the propagation. It's good. It's good, Edward. I like that. Transverse waves have oscillations perpendicular direction of energy transfer. I like that. No, Pranav. They often go on to study biology or geology or chemistry, I guess. Or I don't know. What are those subjects that need you to remember things? So Lex is typing. I hope he's not given up. Medicine. Yeah, that needs memory, doesn't it? I don't do medical physics in my school because almost all of it is just remembering stuff. It's an awful A-level course, in my opinion. Several people are typing. I bet you're all just moaning about biology. Transverse wave motion, which all points on the wave oscillate along paths at right angles. Okay, yeah. Lex, transverse oscillate perpendicular to the wave direction of travel. Good. Longitudinal. Okay, so here's my preferred wording. You've all got such wonderful answers here. This is really encouraging. The trick now is to commit it to memory. So here's what I would answer. I would answer that for longitudinal waves, the particle vibration or the particle oscillation or the particle displacement is parallel to the direction of transmission of wave energy or the direction of propagation of the wave. Yeah, but that doesn't necessarily mean it's right, does it, Edward? Yeah. So I'll say that again. For longitudinal waves, I'm giving you a few options here. So whatever sticks is the option you need. Particle vibration or particle oscillation or particle displacement. Notice I'm giving an explanation of longitudinal waves in terms of particles vibrating. I will allow an A-level student to answer why that is the case. Why am I specifically talking about particles oscillating for longitudinal waves? and then saying that it is parallel to. Okay, good luck. Enjoy your lecture, Pranav. Let me know how it goes. So it is parallel to. I don't say the particles are vibrating in the same direction. I say it's parallel to. It's along a line which is parallel to the direction of, and then I finish it off with transmission of wave energy or propagation of the wave. Other way around, Joe. Longitudinally, yeah. Yeah, okay, James, let me know how you get on. Yep. There are two types of waves that you deal with in A-level physics. You don't deal with probability waves in physics. You do at degree level. I should have said at A-level physics and GCSE physics, there's only two types of waves that you talk about. Mechanical waves, where something's physically moving, and electromagnetic waves, where it's electric field, which is oscillating. But you can't get longitudinal electromagnetic waves. So when defining longitudinal waves, I did it in terms of particles moving. And if I'm defining longitudinal waves in terms of particles moving, okay, see you, 𝗟𝘳𝗧. I'm only going to be another 10 seconds, but okay. Transverse waves, I will also define in terms of particles moving so that you can make a clear comparison between those two definitions. So transverse waves, the direction of oscillation of the particles or vibration of the particles or displacement of the particles is perpendicular or 90 degrees to the direction of propagation of the wave or to the direction of transmission of wave energy. That's what I would give as my answer. And that's it. That is the end of Waves 1. Whoopsie, pressed the wrong button. Right, so, important note, next week, there is no physics with Keith on the Tuesday. I'm going camping with my daughter. It's half term. I think everyone needs a break. And then the week after that, we will do some more in-depth wave stuff. We're going to look at some more applications of waves. Probably going to go a bit more into A-level for the A-level students, but GCSE students, you get so much out of joining in. There's going to be more questions next, in a fortnight's time, next time. There's going to be some more mathematics questions to try yourself out with. So that's why for GCSE students, you can still get a lot out of it. As usual, yeah, great. Yeah, it's good to see you, Edward. So I'm not going to look at all those messages now, otherwise I get distracted. It's really helpful to me. I know it sounds cliche, but it's really helpful to me if you could like the live stream, because that helps boost my ratings. If you're not subscribed and you're watching it for the first time and you think, actually, that looks quite helpful, subscribe. Okay, I mean, you're going to get notifications on every social media platform anyway, but it does help me reach that magic goal of 1,000 subscribers, which is what I need to get in order to embed live streams on my own website. So please help me reach that goal. Yeah, we're on 538 subs at the moment, so we're nearly there. So thank you very much. Have a good week off. Have a rest, because some of you have worked really hard. I will see you in a fortnight's time. Stay safe.